everyone. In this video, we're looking to find electric field due to non-conducting charge sphere and electropotential as well. Okay, so electric field and potential due to non-conducting charge sphere. Okay, this is actually a solid. Okay, in the previous ones we have taken hollow non-conducting charge spheres. Okay, this is solid. Okay. First, we'll do the uniform one and then non-uniform one. So, consider, let's say, this is a sphere, okay, having positive charge Q distributed all over, okay. Now, we need to find electric field at 3 different points, okay. One more thing, let's say its radius is R. So, we have rho is equals to Q upon 4 by 3 pi R cube, okay. The charge distribution is, the whole charge on the sphere is, okay. So, the first one, okay, we'll find when small r is greater than capital R, right? That is outside. So let's say this is smaller, okay. Then we'll draw a sphere, right, of radius smaller outside, okay. This is so, and we'll find the flux, okay. Suppose this is area element TA, okay. So flux passing through this will be d phi is equals to E dot dA, okay. We'll integrate this, phi is equals to E and dA will be 4 pi r square. See, angle between vector E and vector dA is actually 0. Okay, so cos 0. So I'm writing it directly. I hope you understand. Okay. Now, by Gauss law, what will be the flux? It will be Q enclosed upon epsilon naught. Okay, and here your Q enclosed is the whole charge on this sphere, that is capital Q epsilon. So we just need to equate this. Okay, on equating, what we get? We get E into 4 pi r square is equals to Q upon epsilon naught. From here, E is equals to 1 by 4 pi epsilon naught Q by r square. Okay, this is same as for the in the previous one for the non-conducting hollow ones, hollow one. Okay. Now, if we convert this into, if suppose volume charge density is given, then how will you do it? This can be converted. It can be written as rho r cube over 3 epsilon naught into small r square. Okay, you can do it. Okay, you just need to substitute Q as rho into 4 by 3 pi r cube, then terms will cancel out and this will be the answer. Okay, in terms of rho. Now the second one, when small r is equals to capital R, okay, you just need to substitute small r by capital R. So E will be 1 upon 4 pi epsilon naught Q by r square. Okay, and you can write it as rho into r upon 3 epsilon. That means at the surface electric field will be this one. Okay, now when small r is less than capital R, that is inside. Okay, suppose this was our sphere. Okay, inside means, let's say this, at this point we need to find, so we'll draw imaginary sphere there. Okay, now flux will be E into 4 pi r square. I am writing it directly. Okay, due to passing through this. Okay, and by Gauss law, what we get? By Gauss law, we got phi is equals to Q enclosed upon epsilon naught. Okay, now what is Q enclosed here? See, Q enclosed will be rho into this volume, means volume of the small sphere, okay, which is what, 4 by 3 pi into small r cube, right? No, sorry, into small r cube, okay. This is small r and this is capital R, okay, the bigger one, okay. So you need to substitute this Q enclosed, okay, and here, and you'll get the electric field, okay. So E into 4 pi r square after this step, okay, E into 4 pi r square is equal to, this is what, it's flux, and Q enclosed is rho into 4 by 3 pi r cube upon epsilon naught, okay. So 4 by 4 pi gets cancelled out, and if you shift it there, you will get E is equals to rho into small r upon 3 epsilon naught. This is what? This is our electric field inside the solid non-conducting sphere, okay. At the 3 points we have founded it, okay. You can also substitute this rho, okay. You can write it as q upon 4 by 3 pi r cube, and you will get, I think I'll write it, okay. This will be 1 upon 4 pi epsilon naught. That will be multiplied here, so it will be q into small r by capital R, okay, in terms of charge, and this is in terms of volume charge, okay. Now we also need to find electric potential as well, okay. So for electric potential, you just need to draw those figures, okay. uh, we consider uh, a solid sphere, okay. Let's say this is a solid sphere or when charge q, okay. We'll do it via that method, okay. That is change in potential equal to minus E dot dr, okay. That is work done in moving charge, unit charge from finite to required point. The first one, outside, means when small r is greater than capital R, okay. Suppose this is our center, okay. So when small r is greater than capital R, okay, I'm writing it directly, okay. You can also do it. Vp is equal to kq by small r, okay. The second thing, when small r is equal to capital R, this is point P, okay. V will be kq by just a second. You do it by the same approach, okay. I have done it for hollow non-conducting or hollow conducting, okay. Now the third case, small r is less than capital R, that is inside, okay. So consider this, okay. Yes, consider this sphere, okay, inside of radius smaller, okay. Now potential will be, you just need to divide it, okay. It will be v minus v infinite is equals to minus E dot dr. Now we'll break it into parts. The first part is from taking infinite to the surface, okay, and then from surface to the required point, okay. So I'm breaking it, E dot dr from infinite to surface plus E dot dr from surface to our required, okay. So v infinite, it will be 0, so v will be minus. Now you need to write electric field. So see, outside electric field is what? It is kq by small r square dr, okay, plus. Now inside, what is our electric field? Electric field was kq by small kq into small r upon capital R cube, okay, dr from capital R to small r, okay. I think I have written it kq small r by capital R, okay. Now you need to integrate this, okay. This limit was, I think, from infinite to capital R, and this limit is from capital R to small r, okay. Now v will be, that will be alone outside kq by r minus kq by I think it will be 2r cube QR square minus, I'm writing it directly, okay. I think we will be, after solving that integration, we will be kq by 2rq in bracket 3r square minus small r square. This will be the electric potential inside the solid non-conducting sphere. Okay, and at outside, this was our electric potential. On the surface, this was our electric potential. Inside, this was our electric potential. Okay, by the same approach, okay, that work done from infinity to required point, you can solve. We have gotten that result from all these approaches, but I have retained directly because you don't need that much of derivation. Okay, here it this was having a charge q, okay, and linear charge density rho. Okay, this is for the same one. Okay, so that's all. Thank you. And from the next video, we'll do some problems, and then we'll start equipotential surfaces. Okay.